Your solutions to the final exam for ECE 320 Electronics 1. The first problem is draw the load line, then find the Q point for this given diode. The blue line is given, that's the diode. To draw the load line, what I need to do is, at this point looking left, find the Thevenin equivalent. V Thevenin is R over 2000 plus R times 10. For me, R is 1314. And that gives you 3.96 volts right here. The short circuit current is, if I short this, I get 10 volts over 2000 ohms, 5 milliamps, gives you this point. 2 points defines a line. Where it intersects is your solution. So the intersection is going to be right around 2.7 volts, about 1.6 milliamps. On to problem 2. Problem 2 looks at write n equations, n unknowns for the circuit. Don't solve, just give me the n nonlinear equations. For a diode, the voltage across the diode is related, or the voltage anode to cathode determines the current. So for the first diode, voltage anode to cathode is V0 minus V1. The second diode, it's 0 minus V2. The third diode, V3 minus 0. Once I get the currents, I can write the node equations. At node 1, the current left, current up, current down, down, down equals 0. So that's going to give me these 5 terms. Current through the diode, going backwards, current through the resistor, down, down, down. At node 2, current up plus the current down equals 0. Current down is minus ID2. Node 3, the current up plus the current down equals 0. Here the current down is plus ID3. Gives you these equations. So those are the n equations to solve for, the n unknowns. Problem 3 says, assume ideal silicon diodes. Now find the voltages. The trick here is to figure out which diodes are on or off. I've got 10 volts trying to push current to the right, so probably diode 1 is on. This is your birth date. Here, I just chose Mother's Day. This diode is probably off. Diode 3 is probably on. If it's on, it's 0.7 volts. Off means there's no current flow, so V1 equals V2. Now we can write the node equations. At this point, the currents have to balance. So to find ID1, this current plus this current plus this current plus this current plus this current equals 0. I know all these currents since I know the voltages, so I can solve for ID1. And if you do that, ID1 is the sum of these. ID1 is 6.86 milliamps. It's positive, so I was correct. Diode 1 is on. Diode 2 is off, 0 milliamps. Diode 3 is 9.3 minus 0.7 over 2000, 4.3 milliamps. So that should be the answers for problem number 3. Problem 4 is an AC to DC converter. I've got 2 parts, DC analysis and AC analysis. For the DC, I know the voltage of V1 is doing this. It charges, discharges, charges, discharges. The peak will be your 20 volts minus 0.7, 19.3 volts. Doing worst case analysis, the current then is 19.3 volts over 170 plus these 2 in parallel. These 2 in parallel give you 567 ohms. So the current becomes 26 milliamps. Once I know the current, I can find the ripple. From I equals C dB dt, I've got 20 milliamps flowing from the capacitor. It's 120 microfarads, turns on in 1/60th of a second. The ripple is about 3.63 volts. So this distance is 3.63. Now that I know the AC voltage, I can tell you the DC voltage is the peak minus half the ripple, 17.48 volts, and there's the AC voltage, the ripple. Now go on to V2. At DC, this is 567 ohms, capacitor doesn't matter, inductor doesn't matter. I've got a voltage divider. 567 over 567 plus 170, R1 over R1 plus R2, times the DC voltage, gives you V2. For the AC voltage, same thing. I now add the capacitor. The capacitor is minus J132 ohms, that's at 60 Hertz. The inductor is J1885 ohms. Put these all in parallel, gives you 29 minus J125. There's your R1, here's your R2. The voltage at V2 is your R1 over R1 plus R2 times the input. This is the input voltage. Gives you 0.265 volts peak to peak. Problem 5 is a max-min circuit. Find the currents. The first step is to figure out which diodes are on, which ones are off. So one of these two will be turned on. Turns out it's the min function. If I assume this one's on, I get 9.7 volts. That's too much. Both diodes are on. I can't have two diodes that are in parallel both on. So this one turns off. Over here, this is also min function, making this 4.7 volts. Now in the middle, the diode on the left turns on. So I have 6.7 minus 0.7, making that 6 volts. Pushing current backwards through diode 4, turning it off. That all works. Now to find the currents, I've got 6 volts going to ground through 1314 ohms. That tells me that I3 is 4.5 milliamps. I know that this current down here is 12 minus 6.7 over 400. 4.5 goes right, the remainder goes left. So the remainder will be 8.6 milliamps. And over here on the right, 12 minus 4.7 is 18.25 milliamps. Well, 12 minus 4.7 over 400 is 18.2 milliamps. That current has no place to go except diode 6, so it all goes through diode 6. Problem 6 is a load line. Given a BJT transistor, draw the load line, find the operating point when Vn equals 6 volts. So for the load line, the x-intercept will be right here at 11 volts. The y-intercept is 11 over 50 to 20 milliamps. Connect them and get a straight line. The base current is, if this is 6 volts, on the right side is 0.7. Again, this arrow means diode. 5.3 volts across R gives you IB. Guess I didn't do that. Once I have IB, it's like 4.2, 4.03 milliamps. Here's 4, here's 5, here's 4.02. There's my operating point. So BCE will be about 2.9 volts. IC will be like 161 milliamps. Problem 7 is to design a Schmidt trigger that turns on at 1500 ohms, turns off at 1300. So this is, again, your birth date. For me, it's 1314 ohms. I just use Mother's Day. So if I do that, I want to turn on at 1500 ohms, turn off at 1300. With a voltage divider, I can calculate the voltages. So I want to turn on at 5.33 volts and turn off at 4.79 volts. The on voltage is more than the off voltage, so connect the plus input. I turn on at 5.33 volts, that's my offset, and the slope is the gain. Output changes by 10 volts as the input changes by 0.5, gives you 27 to 1. That's your 27 to 1. Now going on to the amplifier. If I want to have 100 milliamps flowing, the transistor has about a 0.2 volt drop across it when it saturates. This is a 3 volt drop at 200 milliamps, being a diode. It's also 3 volts at 100 milliamps. Diodes kind of have this characteristic. Whatever the voltage drop is at 200 is basically the same voltage drop at 100. That's an ideal diode model. So this is 3 volts. The total is 3.2 volts. 10 minus 3.2 over 100 milliamps gives you 68 ohms. And then for the base current, if this is 100 milliamps, beta is 100, the base current has to be at least 1 milliamp and can't be more than 25 because that's all the op-amp can do. Pick a number between 1 and 25. I chose 9.3 milliamps, so when this is 10 volts, this is 0.7 volts. 9.3 volts across 1K is 9.3 milliamps. and that's the valid solution, something between 1 and 25. Problem 8 is Dtologic. Given the input voltages, find the currents and voltages. Well, in the first case, both these are 5 volts, so the current is going to go right, probably saturating this stage. When it saturates, this is 0.2 volts. On the bottom, I've got 0, 0, so current's going to go left, making this 0.7. At 0.7, that's not enough to turn on this transistor, so it turns off, becomes 5 volts. On the right-hand side, if this is 0.2, this diode turns on, making this 0.9. Not enough to turn on these diodes, so they turn off, and the output will be 5 volts. To find the current, and this is 1314, 5 minus 1.4 over 1314 gives you 2.74 milliamps. This diode is off, so the current is 0. And this one's off, that current is 0. So these should be the answers. V1 is 0.2, 5, 5, 2.74, 0, 0. Problem 9 is a load line for MOSFET. Okay, the x-intercept will be 12 volts. The y-intercept is 12 over 70, about 172 milliamps, 171 milliamp. 2 points determines the line. If VG is equal to 7 volts, I have to be on this line somewhere, so there's my solution. It's going to be about 115 milliamps, about 3.8 volts. And I'm in the ohmic region. An ohmic region is everything to the left of here. And over here is saturated. And the last problem is a CMOS gate. Implement this Carnot map using CMOS logic. I prefer circling the zeros. You can circle the ones or zeros, either way. If you circle the zeros, you get the logic for the low side. So if I have these for the zeros, I get Y bar, since I circle the zeros, is A and C, or B and D, or A bar, C bar, D. Using De Morgan's law, this is Y. So to implement it then, this would be Y is pulled low, when A and C are true, or B and D are true, or A bar, C bar, D are true. On the high side, that's De Morgan's law. Series becomes parallel, parallel becomes series. So these two in series become A and C in parallel. B and D in series becomes B and D in parallel. A bar, C bar, D becomes A bar, C bar, D in parallel. And put all these in series. So this implements that previous logic. And that's the final exam for ECE 320.